Brain-encoder models predict cortical fMRI responses from AI activations, but held-out prediction accuracy is a poor interpretability signal. It confirms a fit without revealing if the encoder internalized functional organization. To bridge this gap, we use feature visualization, gradient ascent on the encoder's predicted activation for a target region of interest. This synthesizes inputs that maximally drive that region, offering a qualitative probe of cortical selectivity. We apply this to tribe V2 composed with a V-JEPA2, V-TG backbone. The results recover known cortical hierarchies with striking fidelity. In the ventral stream, optimizing V1 through V4 reveals a clear progression of increasing spatial scale and feature complexity. V1 produces dense Gabber-like edges, while V4 organizes mid-scale curves. The middle temporal area, MT, is canonically motion selective. Yet optimizing static images yields sharp radial streaks resembling frozen optic flow. This indicates V-JEPA2 learned feature directions for implied motion, and tribe V2's readout successfully captures these static motion cues. For the fusiform face area, FFA, the probe generates face-like features. Crucially, the optimized stimulus drives, FFA, roughly 4 times harder than a natural face photograph. This is the superstimulus effect. The optimizer exploits the feature space to find adversarial patterns that hit face-tuning directions more intensely than biological reality. The takeaway is clear. Prediction accuracy is necessary but insufficient. Feature visualization demonstrates that tribe V2 has recovered the input-to-region mapping of cortex, capturing tuning signatures without explicit supervision. This differentiable probe provides a cheap, default test to distinguish encoders that internalize neuroscience from those that merely predict it.